So thank you so much for inviting me to this symposium and for giving me this opportunity to speak here. I want to use that opportunity to reflect on a question that I think is central to AI and certainly has been the basis of now more than 10 years of collaboration with and inspiration from Eric. And the question that I want to discuss here in the session on learning, decisions, and intelligence is, what do we need to learn in order to decide? Or in other words, what information do we need to collect in order to act effectively on it? And this question is central to many different domains and applications. So one classical one that's been obviously motivation is medical diagnosis. Right? You have a patient, you just need to decide how to treat it, and you have to decide what tests you might want to do on the patient in order to collect just the information you need to make the right decision. There's many other applications where you place sensors to detect fires or contaminations, which experiments do you conduct in the pursuit of new materials, which of the million unlabeled examples do you label in order to train effective classifier, what information do you collect about users in order to make effective recommendations, and many, many others. So this is a really central question of high relevance to applications. And there is a principle, there's different ways of, what is the text up there? It's also showing up here somehow. This is not part of the slides. Can we maybe get rid of it? That would be nice. Okay. Not the entire slide, though. Anyways, I can try to do it without the slides, too. But OK, so basically, there's many different ways of thinking about this problem. But one particularly elegant way is this notion of value of information. And this is setting that we have to act upon some unknown quantity y, say the state of the patient, by carrying out some action A. And depending on what state y is in, what actions we take, we get some utility. Trouble is we don't know what's y, as we can only make predictions about it, right? And the value of information quantifies how useful it is to acquire certain information X in order to... What is this? Okay, in order to act effectively. Can I use my laptop, my own?
Technology for you. It is the future.
Okay, all good. So very good. So basically, the value of information is the extent to which our knowledge of X allows us to act better on that information. So the value we can get knowing X compared to the utility we can get if we don't know X. Okay, and so this is a beautiful, elegant concept that allows us to reason about many applications, but to get it to work, it's actually quite challenging. There's lots of issues with computing it, estimating it, optimizing it, and applying it in different settings. And so some of these questions I started to think about during my PhD. And one of the first papers that I read there that's really shaped my thinking was this beautiful paper that Eric wrote together with David Hackerman and Blackford Middleton on an approximate non-myopic computation of value information, where they laid out this elegant approximation for calculating the value of information for sets of observations to get at the same time. So I was terribly excited once I got the opportunity to actually come to MSR and get to work with Eric on topics related to value of information. So I super well remember our first discussion, sitting down, brainstorming about ideas, and I can only echo what Sue and Rick presented before. It just, I mean, all that creativity, all these amazing ideas that Eric laid out. We came up with a long list of research topics, I think, that would fill several academic careers. So one question that in the end we settled and actually worked on was to think about value of information in the context of privacy, in the context of private information. The motivating application there were personalized online services, personalized search, right? You want to make a prediction about the user's intent, say the page they want to go to, given a query. And the more information X we know about the users, the better we can diagnose, right, to make that decision. On the other hand, of course, we want to be careful as possible with sharing private information, right? And now we can think about this in terms of a utility theoretic point of view, where we on one hand side have the value of information in terms of these observations, like demographic attributes, past search behavior, etc. we might get, while at the same time contrasting it with the sensitivity of sharing this private information. Okay, and so that gives us an objective which we can optimize, that has some nice structure that we looked at in the paper together. It turns out to be a modular optimization problem. There's some good algorithms for solving it. So one of the topics we looked at there, for example, is there's sort of this value of information, one inside the different units. There's this sensitivity risk, quite different units. So how do you really put them on same terms, right? So we thought about careful studies on how to use search logs, how to ask people about their preferences in order to calibrate this trade-off, and these are some of the plots from the paper that we eventually published on this. So it's sort of a nice opportunity to talk about some older work here, but it's been a really inspiring project. So another topic that we got to work on in that few months basically was thinking about private information in the context of community sensing. So all of us are carrying around lots of sensors these days, so in their smartphones and their watches, etc. And harnessing that sensor information could be tremendously valuable for society. So the problem we looked at about 10 years ago now was to think about traffic prediction, right, using GPS information from mobile phones and sensors. And we thought about how can we do this in a privacy-preserving sort of manner, right, to really carefully only request information when it's actually useful in order to make predictions in places where it's most needed. So we thought about how to formalize this, how to ground it in this framework of information, and think about algorithms in this context. Okay, so these two projects are really tremendously exciting to work on, a lot of fun to collaborate on, but also really were the spaces of a space of problems that just waited to be explored. And in the years to come, my research group and I have really followed up on a lot of these different ideas that really were tremendously inspired from these discussions with Eric and his experiences in it and here at Microsoft. We looked at algorithmic challenges in this context, developed some new algorithmic ideas there. We went beyond privacy to think about other human aspects, societal aspects of value information. For example, thinking about incentive issues in this context, notions of fairness. I'll talk a little bit about safety. And also think about a whole bunch of different applications in the context of community sensing. So we did a project on doing earthquake detection with mobile phones, for example, but also applications in the sciences. So in the just remaining 2 minutes or so, I want to talk about one recent project that's been really inspired by this, thinking about the notion of safety in the context of information collection exploration. Okay, and so there's a lot of interest these days in RL, fueled by some of the recent successes in this area. And of course, that's this model where we need to make decisions in order to affect an environment and derive some reward from it. But the agent who needs to make these decisions doesn't know how the world works. That means the agent needs to explore to figure out what's the consequences of the actions that they're going to take, right? And if we train reinforcement learning agents in simulation and we have enough compute power, then we can really do unconstrained exploration. But if you think about embodying reinforcement learning in real-world system, then exploration is a potentially dangerous environment, right? It means we have to try things that we haven't tried before, right? Which can be a recipe for disaster. And I've been really thinking about quite a bit in recent years on how to sort of ground ideas of information gathering, exploration, active learning in the context of safety and reliability considerations. So one particular motivating example was actually a medical application in the context of medical rehabilitation. I won't have so much time to talk about this, but I just want to talk about one concrete demonstration in a sort of a stylized robotic application where we have this robot, this quadcopter here that's supposed to solve a simple task, fly from A to B. It has some sort of initial policy, initial controller that gets the job done, but it's not very good. And so now what it wants to do is it wants to explore its own space of control parameters in order to learn to get better at that task. That's the common issue in reinforcement learning. But the problem is that a lot of these parameters really could cause the system to become unstable and crash against the wall. Right? And now the question is, how do you think about this problem in a way where you can sort of do cautious exploration to sort of try to push the boundary, expand what you know about where you can go and where you can further explore, while at the same time trying to optimize the performance. And we've been thinking about this algorithmically, developing algorithms you can actually analyze under certain conditions, you can actually guarantee safety and some notion of completeness, sort of being able to find optimal actions in this context. So this is one instantiation of this value of information idea that's been very much inspired by these past interactions. Okay, so this brings me to the end of this short talk. I think this notion of value of information is really one of these principles of intelligence here in the spirit of this symposium, right? And it really relates to some of the big open questions that we don't really have a good answer for at this point, right? Sort of how do you evaluate and put the price tag on data sets? How can you incentivize sharing of data for the social good? How do you balance the value and benefit you can get out of data, at the same time taking into consideration privacy, fairness, and safety? And even more broadly, how do you think about conceptualizing and formalizing and automating notions such as curiosity and serendipity that are also integral parts of the scientific process? So with that, I'd like to conclude and just take this opportunity once again to thank Eric for all the mentorship and guidance he's given over the years and for allowing me to become part of this amazing community. Thank you, Eric. Good. So we're moving on to the next talk by Dafna Shahaf.
Okay, so hopefully I'm not going to have any crazy soap opera subtitles. Okay, can you hear me all the way to the back? Perfect. So hi, I'm Dafna, and Eric and I have been working together since my first year of grad school. I came for an internship that turned into another internship that turned into a bunch of visits that turned into a postdoc. Overall, I kind of suspect that I went through the Microsoft orientation process more times than any person alive. Now, when I was preparing this talk, I tried to reflect on why do I keep coming back? Like, what makes this collaboration so much fun for me? And I think I realized something. And I realized that Eric and I have been playing a game for the last 10 years. It's actually a pretty famous game if you're into improv comedy, like Whose Line Is It Anyway? It's called Yes and. How many of you know this game? Okay. Oh, more than I expected. Basically, one actor says something, and the other actor has to follow with yes and elaborate on the initial statement, no matter how crazy it was. And this is kind of how we act, because I can come back from a conference and tell Eric, you know what, you wouldn't believe it, I ran into the New Yorker's cartoon editor, and he's awesome, and he has data, and he's willing to share the data, and I'm going to work on cartoons for a while now. And instead of telling me that I'm drunk, Eric would say, yes, and let's fly him over, and let's bring gaze detectors, and let's run an experiment about how people interact with cartoons, and go in all those crazy directions. And it will actually end up in a paper that we have with the New Yorker's cartoon editor. Let me give you another example. This is one of the first papers we wrote together, Investigations of Continual Computation, submitted to IJCA. You can see it's anonymized. And I was a young and idealistic grad student, and I was complaining to Eric that the whole double-blind thing makes zero sense, because you spend 5 seconds searching continual computation, you know who wrote this paper. And instead of telling me something like, yeah, but you know that's how the system works and deal with it, Eric goes, yes, and we started talking about it, and this was the birth of Eric Horvitz. We actually submitted the paper with his last name misspelled in the reference, because maybe the reviewers will say, well, maybe it's not him after all. I mean, he can't even spell his own name. In case you're worried, we actually fixed it for the camera already, but we did submit it like this.
This is actually Uta Pro's idea.
Was it?
He spelled his name P-E-R-L in reviews of people's papers.
Okay, so I told you a little bit about how we work. Let me tell you a bit about the work that we actually done, the research. Okay, so switching gears, breathe in, breathe out. Okay, so Daniel Gilbert is a Harvard psychologist, and he used to say that just like physicians have the Hippocratic Oath, psychologists also take an oath. And they swear when they get a PhD that at some point in their career they're going to publish an article containing the sentence. And the sentence goes something like this. The human being is the only animal that. And it's up to them how they want to finish it. Now, he's clearly joking, but there is some truth to it, because over the years there's been thousands of papers published with some variant of this, right? We had the human being is the only animal that has language skills, until chimpanzees started doing sign language. And then it was, well, but we're still the only ones that can use tools, until scientists showed that even birds can use tools. So what I'm trying to say is that early on, this battle for mankind's sense of uniqueness was waged against animals. But recently, it's more and more against computers. So you hear things like, well, but we're still the only ones that will ever be able to play chess or Go. And, well, we all know how well this is going for us. Right? So what I'm saying is that even today, there are still many areas that are considered to be outside the scope of computer science, what I call soft concepts in the title of this talk. Like computers will never be creative, computers will never have a sense of humor. And I'm going to argue that those are the most interesting areas to do research in computer science in. First of all, because they're fascinating, but also because every time you make progress in one of those, it pretty much directly translates to improvement in how we can collaborate and interact with computers. So I'm going to spend the next of the talk telling you about my favorite two approaches for tackling those soft concepts. One is the axiomatic approach, where you take a soft concept and try to formalize it mathematically, craft an objective function that simulates your intuition. And whenever this is difficult, we have the data-driven approach, where you use data to guide kind of your search for an objective. Okay, so axiomatic approach I'm going to demonstrate with a project called Metro Maps of Information. And this is a metro map. It's a structured summary of a complex story, okay? So it's really visualization. Each line is a coherent narrative thread. Different lines focus on different aspects. And you're supposed to look at it and get the big picture, in this case about the debt crisis in Europe. So what we did is we actually looked at what soft concepts are involved. Coherence, for example, each line should be coherent. The map should cover important things, be diverse. If two lines are connected, the map should reflect it somehow. And we formalize it mathematically. Not going to go into the details, but I just want you to know that we had an algorithm that actually solves this mega objective. And we actually did this and computed maps for news, scientific papers, core decisions, and finally, just for the fun of it, Lord of the Rings. And I'm actually going to take this opportunity to tell you about one more of those, yes. Okay, you know what I'm about to say. I'm sorry. So this Metro Maps was actually my PhD dissertation. And Eric was on my committee, and he had to fly to CMU for my defense because the CMU rules were stupid this way. And I don't know how many of you know the Gates building of computer science. It has this weird like spiral thing going, I think like 4 floors tall, something like this in the middle of the building. And Eric saw this, and his immediate reaction was like, this looks like a cool place to skate. And this was my turn to go, yes, and what's your shoe size again? Which resulted in Eric going down the helix, you know, all the 4th floors, luckily without killing anybody. So it was fast. It was faster than I expected. Okay, that was the axiomatic approach. Let me tell you about the data-driven approach. And this is the project I started telling you about with the New Yorker's cartoon editor, Bob Mankoff. So the New Yorker holds this cartoon caption contest. How many of you know it? Okay, good. So they publish a cartoon without a caption. They invite readers to suggest their idea of a joke or punchline. They get thousands of suggestions. And our goal was to take those thousands of suggestions and rank them automatically, funny to not funny. Not perfectly, I'm not saying we solved the humor, but in a way that will reduce the workload of the judges. So I tried approaching it like Metro Maps. Okay, let's formalize what makes a caption good, what makes a caption funny, and this was just going nowhere. Okay, so I said, okay, let's try to use data. And we constructed the Dataset. We actually took a bunch of cartoons like this one. This is actually one of my favorite ones. There's this car salesperson that tries to convince this poor couple to get into this thing that's kind of part car, part monster. And we went to Mechanical Turk, and we showed people cartoons with some potential captions. For example, okay, take a second and look at this cartoon. So it's a hybrid. Or an alternative, just don't kick the tires. And we asked him which one was funnier. And we actually collected hundreds of thousands of judgments. We used them, extracted lots of linguistic features. And we trained a classifier and came up with a ranking. And actually showed how the best captions propagate to the very top of the ranking. Okay, I'm going to spend the last 2 minutes telling you about my favorite 2 challenges, my favorite 2 holy grail kind of soft concepts. One of them is creativity. We actually did some work recently about how to make people be more creative when they come up with ideas for new products, mostly through analogy mining, through showing them ideas that are in very far domains, but that share some abstract similarity. And the other is my old nemesis, common sense. And the reason I'm bringing both of those up is mostly that I actually believe that this is not going to be solved by just, let's collect an insane amount of data and throw a neural network at it. Okay, that we'll actually need to come up with something more clever. Okay, and I'm going to finish with a quote by Jeffrey Hammerbacher, who said that the best minds of my generation are thinking about how to make people click ads. That sucks. Okay, and I completely agree, and I encourage you to go chase some of those soft concepts, and if you have ideas, come talk to me later. That's about it. Thanks, and happy birthday.
The introduction, Dafna.
Hey, no, friend. You're supposed to do the intros. This is Ashish, everybody.
Yeah. Hello, everyone. So I've been working with Eric last 12 years. So the history is that I was supposed to be in Redmond only for a year, but I'm here after 12 years and still continuing to be here for, I think, few more years. But let me tell you about some of the work that we've been thinking and how it has been influenced by, by my association with Eric. So specifically, we've been thinking about decision theory for a long time. In fact, decision theory was a word I heard, for the first time in detail from Eric when I first started my postdoc. We did all machine learning and pattern recognition, and no one talked about decision theory in a computer science class. So one of the key ingredients of a decision-making model is, the model of the world. Any robot, any intelligence, any decision-making service needs to have this model where it can test its hypothesis. It can be a set of rules. That's how we started. It can be influence diagrams. It can be data sets. It can be neural network that have been fitted on those data sets, or Bayesian networks, or probability distributions. And if you're very fancy, you can even think of probabilistic programs. But again, these are just models. What we've been thinking recently is, what would happen if you replace all of this with simulation, right? So what's the difference between simulation and a model? So what a simulation is basically a conjunction of models together with the program. So far when we think about machine learning, we are fitting models to it. But we also want to see what happens when you apply algorithms to it. So all the rich synthesis of the data is what the simulation is. And the hypothesis here is that when you start thinking about simulation in the context of a decision-making service, it's going to profoundly change the ways we think about decision theory. So the idea is build a model and run a simulation. And so far, we've just been building a model. That's what I would argue. And now let's think about running a simulation. So I'm very thankful for Eric for sponsoring this work. When a couple of years ago, when I said, hey, I want to do robotics, a bunch of folks in Microsoft asked me, like, are you out of your mind? We just let go of a bunch of robotics folks. Why would you want to do that? And Eric was very supportive, and he helped me hire Sheetal, who basically ended up building what this is called AirSim now. And the whole idea is that let's create a model of world in simulation. This is video game on steroids, except the video games are being played by software agents. So these are machine learning system, decision theory, theoretic services. You can create rich models of cars and people and all the phenomena that happen in the real world, including weather, time of day. You can create factory flows. You can create simulations of each and every sensors that you think will be part of your decision service. And you have something like this, a portal like that. What can be enabled? Again, it has already, I would say, have a significant impact on how we think about robotics personally in the group. But we are expanding that thinking to decision theory as we move forward. So again, simulation has impacted a wide variety of field across. If you look at the history of simulation, it started 300 years ago by some mathematicians, and since then, medicine, meteorology, chemical engineering, flight simulation, robotics these days. So it has been a cornerstone in advances of engineering as we moving forward. And the question that we are really asking is, what is the role of such large-scale simulations in building automated decision-making systems? So the first consequence that everyone is aware of is data generation. Like there's a dime a dozen startups that are doing data generation for self-driving cars, right? In fact, we have seen success of such simulation recently in reinforcement learning, where these are simulation of games such as Go, Atari games, or Pac-Man. You can actually use the same concepts. Well, the video is not playing. Let me see. Okay, I'll just go back. So this is a video of a car doing reinforcement learning. Again, the whole idea, video game on steroids, backed up by these reinforcement learning algorithms that can generate data. You don't need to just do supervised reinforcement learning. You can also do supervised learning. This is a very typical pipeline of say, a self-driving car where you have sensing, some kind of a mapping, and a planning. Each of these boxes can be machine learning boxes, but you can actually use data to generate it from simulation. So for instance, in this case, we are collecting data while driving in a simulation, so as to train a neural network that can infer depth map directly from your stereo pairs, right? And you can do some sort of real transfer. So this work was done by by Debugging, who's in the audience, upon insistence of Eric, like, oh, we really need to showcase a sim to real world demo, and this was one of the work that we did at that time. But the second consequence is really visualization, right? If you think about it, if you have a portal like a simulation, you can actually use it to see what your decision-making service is actually thinking about it. But some of these decisions that we are making are so complex that we need a debugging, a viz platform. And so this is again a still from a sim where you can actually see what your self-driving car is seeing. And I know Eric is very fond of his Tesla, and they are very, very interesting simulations there in itself that actually tell you what the decision-making service is going to do, and which can be very important as we move forward. So that's the second consequence. The third one, which has been, I would say, I think is going to be one of the more important paradigms in simulation decision-making, is the whole idea of bringing active learning. So some of our work in early, in 2010 or 11, centered around active learning, centered around lifelong learning. And the whole idea was, how can you generate a set of data points that would be most informative towards building a machine learning system. So you can actually take those ideas and you can say, give me those simulations that will break my black box AI systems. So similar to active learning, you are now really thinking about falsification and verification. Since you have simulations that can generate data, it can be fairly important to ask these kinds of questions. One of the things that Eric has been thinking a lot these days, together with a bunch of colleagues at Microsoft Research, is fairness and transparency. And here is, again, some of the work that we've been thinking that has been influenced by that work, is the whole idea of generating simulations that can break a system. So basically having a blind spot. So for instance, consider the problem of face detection or face recognition. And we know that there are biases in the data. So what you can do is, if you have a simulation, you can actually try to ask the same question: what are the simulations that break my black box AI system? So for instance, if I have a face simulation, so again, this is a simulation that we have created, you can use active learning-like methods to generate cases which will indicate what are the blind spots of the system. And you might be able to then detect, what are the problems, what are the misses in your pipeline that are leading to these kinds of. So it can be a very important reasoning tool. The fourth consequence is really about simulation embedded reasoning. So Andreas showed some work about safety, right? The reality is this: any of these machine intelligence and machine learning methods, they are never going to be foolproof. So we need an understanding of when they are going to fail. So consequently, the whole idea of simulation embedded reasoning is pretty much model predictive control on steroids. So again, this is these ideas are from discussion with Josh Tenenbaum. So the whole idea there is that if I give you a table with a bunch of blocks, and you have to predict what blocks are going to fall down when you shake it. The traditional machine learning approach, what we have been following so far, is really, shake the table 1,000 times and maybe record it and then fit a neural network or machine learning model to it. However, if I have a simulation, I don't need to do that. I can basically create that model in simulation and just do it once, and I have the answers for that, right? So basically, this is model predictive control on steroids. And so the whole idea is that, consider a case when I have an intelligent agent that's trying to navigate in a world, and it's trying to be safe to do that. What you can do is you can have some kind of proposed trajectory, and you can have some beliefs about the world. And again, you can invoke the paradigm of simulations, which is now nothing but you can think of it as a program synthesis problem, but in a probabilistic world. You can generate 1,000 of these programs, and you can sample through all of these worlds in order to assess your probability of how well are you going to do. So you are now generating simulations on the go as you're making decisions. And again, many of these works were influenced by some of the discussions that Eric and I have been having. To the end, we think about this portal that's always running. As the robot is evolving in the world, it has access to these simulations. And before carrying out any decisions, it basically calls on in simulations and asks the questions, whether does it make sense for me to carry out these actions, for instance. And finally, if you have a portal, something like that would enable you to build decision-making systems in software, it would help us with the democratization. If you are a roboticist right now, you know how hard it is to build real-world robots. But if you have a software portal where you can do all this training, development, verification, validation, falsification in software, all this technology becomes very accessible to a lot of people in the world. So with that, I'll conclude. So, the whole idea is that simulation will be key to automating decision-making in the real world. That's the hypothesis that we are following. Many open questions. The first thing is, how realistic should these simulations be? Again, the thing is, you can actually think that when we operate in real world, we do have a model of world and we are simulating all of these things in our head, but it's not as high fidelity as the real world. So there's a question of fidelity. How efficiently can we generate some simulations? And also we have to do inferences and learning in the simulations. So, I learned with the snapshot of building 99 simulations, so possibly most of you who have interned or worked there are familiar with. We have created the entire simulation of the building in building 99, and the hope is that we can interface such simulations with some of the thought-provoking ideas, such as situated interaction, as well as sim to real, etc., in order to push the envelope forward. Okay. Thank you. All right. So
Thank you, Ashish. So the last talk in the session is given by Mohsen Bayati.
I see them here. Okay. And does this work? Okay. So actually, this is where I'm going to start. I'm going to make this short talk about one project which is motivated with this paper, and I'm going to give a history of this paper. So I was a theory postdoc in my MSR about 10 years ago, and I remember Mark Braverman and myself, we were both theory postdocs. We came to Eric and said, we want to work on healthcare applications. Can we do that in Microsoft? And it was actually in this building, in TechFest, that Eric introduced us to Michael Gillum, who was working in the Microsoft Health Solutions Group. They were in DC. They had pretty much 7 hospitals' data. It was a startup that Microsoft had acquired, and they were trying to build solutions for the healthcare space. And that was like a very good opportunity, because we very quickly went through the security process, get access to all the data, and started working with Eric on this. And one of the first questions they asked us, okay, we have this problem of hospital readmissions, patient coming back to the hospital in a short amount of time. That is a problem. Hospitals are going to be penalized for it. Can you predict it? Because if you can predict it, then we can do something to reduce it. And we ended up, it was a very quick project. Actually, in a few months, we had a solution that we were able to make predictions and also make recommendations, basically based on the risks. You would say some patients have a higher risk than some other patients, and then if the patient has a higher risk, then you allocate more expensive, effective treatments to them. So it was you can think of it as a resource allocation solution in a hospital where expensive treatments are limited. And that pretty much shaped my thinking. Like, I was a theory person, and then this project pretty much changed, I would say, my career. I've been working a lot on theoretical and applications of problems in this space. And what I'm going to be talking about today, in fact, is one of those theory topics and with some applications. So this is actually the pipeline that Eric convinced us to look at the problem this way, and it was very helpful. So we have data, hospital data, use that to make predictions, and then use those predictions to make decisions. And in this case, predictions would basically mean, so this is just some fake data, patient names, everything is fake. So we have, say, 2 treatments, and then predictions are going to be these numbers, a risk score for every patient, and then depending on the efficacy of the treatment, for example, treatment A could be send a nurse to patient's home, treatment B could be, say, do nothing, or could be send a pharmacist to patient home. So depending on the efficacy of these treatments and their cost, you could have some numbers that are listed here. So those numbers combined with predictions will help you make the final decision. And so one thing that came up when we were talking to the hospitalist was most of the time these treatments were new treatments. They haven't been tested before. So the assumption that the model had was the treatments are known, you know how effective they are, you know their cost. But this was not really true. You didn't know this in practice, and you had to really experiment. And the other problem that actually Eric brought up, and it was something that most of the systems that are even currently implemented in hospitals ignore, is that as soon as you make a decision for a patient, then that patient becomes a new training sample to be used in future training and application of the system. So we have this feedback, and that feedback breaks this second assumption that training data is IID samples, because our decision changed the future training data. And how should we think about this? So these two, I should say, we built this system actually implemented, this system was implemented in several hospitals around the world. And right now there are many companies selling solutions like this, startups in this space. But pretty much all of them are relying off of like this, especially second assumption and also the first assumption. So in fact, the easiest thing, like we would always tell to fix this problem, is run an experiment. For a subset of patients, randomly allocate treatments. You're going to have IID data. You're going to actually also use A/B testing to get the effect of the treatments. So the easy fix is run A/B testing. In fact, as we know, healthcare is a highly risk-averse space. Like the moment we would say, let's run a randomized study, all the doctors and nurses would say, no, you can't do that. That's almost impossible. And in fact, unless it's a FDA-approved clinical trial, which is very expensive to run, otherwise it's almost impossible to run an experiment. We know, motivated actually by this fact, multi-arm bandits are introduced. If you want to think of the world as this spectrum of, on the left, risk-neutral, on the right, risk-averse, so multi-arm bandit, you put 50% of the patients on one treatment, 50% on the other treatment randomly. So half of the patients are potentially getting the inferior treatment. And multi-arm bandit, this very famous result of Lyon Robbins, where they introduced a UCB algorithm as well, says, you know, you don't need to put 50% of the patient in the bad treatment. You only need to put almost log n over n fraction of patients to the inferior treatment, and it's going to work. So, but then still, you need to do some randomization. You need to, multi-arm bandit is still making some experimentation. So, but the systems that we are building, or people built in practice, they don't do any experimentation. They're all based on what we call greedy decision making on the far right. So at any moment for any patient, make the decision that you think is the best for that patient. And the question is, will this work? Don't we have a problem? The problems that we listed in the previous slide. And in this talk, I'm going to talk about the fact that there is a ton of exploration in the features. Patients are different. There is randomness in their attributes, and we can leverage that to do less exploration. So just to make this very quick, imagine each patient has a feature vector, and then like the most formal way of looking at this is, in fact, borrowing from contextual bandit literature, expected reward of treatment I or arm I is this function with unknown parameters, and our goal is to learn the parameters. If you know the parameters, and most of our generalized linear models fit into this framework. And just to summarize, so we have k arms, k parameters, IID patients, and we are assuming the rewards are given by those functions of the dot product. So you can think of that visual form on the left, where if a patient is on the left side, you choose treatment blue. If a patient is on the right side, you choose treatment red. And the difficulty is you don't know the two true vectors. You can just estimate them. And then the metric is this regret, which is what's the best you can do if you knew the true vectors versus the decision you made. And the goal is to minimize that number. And that's basically the fraction of the opportunity cost, the fraction of rewards you lost by experimenting, roughly. And so just to rephrase, so the greedy algorithm in reality is something like this. At the beginning, even with the greedy algorithm, you need to do some forced sampling to get a small amount of data. But M is going to be a fixed number, so you don't do any experiment afterwards. Solve the maximum likelihood solution, and then use those estimates to make the greedy decision. And this chart demonstrates this fact that IID assumption is broken. So these X feature matrices the new row depends on the past rows. Therefore, they're not IID anymore. So we cannot even analyze, do this converge? Do these betas converge? Beta hats converge to the true parameters or not? Even for the most simple, like least squares, it's not true that whether they would converge or not. So you need to actually develop a new way of analyzing their convergence, which is what in contextual bandits people have done to some degree. So there is a bunch of assumptions here, which is a standard in the bandit literature, but the bottom one is the one that we introduced, which is what we call covariate diversity. And what intuitively it says you're going to get patients pretty much all over the space with some positive probability. Of course, I'm making another assumption that this is after you've done the feature selection, meaning there's no redundant feature. So the covariance matrix, so this is like a covariance matrix, but conditioned on any random direction. Now, that's like a weird assumption. Looking in the paper, we give sufficient conditions that a lot of distributions, Gaussian, all like mixtures of Gaussian, combinations of Gaussian with discrete uniforms, like various distributions will satisfy this condition. Now, why do we introduce this condition? So the first theory result we have is if you have just 2 treatments and you have this condition, then greedy will actually work. You don't need any exploration. Then the second result says if you don't have those assumptions, then greedy still succeeds, but with a with a probability that, of course, goes to 1, depending on how many forced samples you did at the beginning. But the biggest problem that a lot of people don't like greedy in the bandit literature is that when it fails really bad. It has a linear regret. So we have an algorithm. So this slide tells us we have an algorithm, greedy, a simple algorithm. When it works, it's great. But when it doesn't work, it's terrible. But we also know with positive probability it works. How can we actually operationalize this and do something that is useful? So for the lack of better word, we introduce this greedy first algorithm, which says start greedy, but check in the data if the greedy is failing or if the condition covariate diversity is failing. If it is failing, we run a hypothesis test, and that's based on, because we do see the covariates over time, and based on that, you're going to switch to a bandit algorithm where there is guarantees for it. So formally, this is the algorithm. So step 3 is where the hypothesis test is done, and we are switching to this version of like OLS bandit, but in reality, you can switch to any of your favorite bandit algorithms, UCB, Thomson sampling, anything. So the main key factor is check the data before you actually switch out of greedy. Stick with greedy as well. And the benefit of this is that positive probability that greedy works, you're going to not switch out, but you will switch out when it's going to be terrible. And we also prove that this greedy first achieves a regret of order log n. So this all looks theory. We actually checked how this greedy first compares in a medical application. So there is this very nice publicly available data sets that patients are dosed in 3 dose buckets of warfarin. And we think of these as 3 different treatments. And in this data, you actually know the true dose of each patient, so we can use that to test various algorithms. And there's about 93 features, genomic, demographic, comorbidities, etc. And we look at a very simple reward function. You can put the cost of bleeding and a stroke into account to have a more accurate cost function. But we looked at a simple cost function of the number of incorrect decisions, the number of incorrect initial dosing of patients. And this is, so y-axis is the fraction of incorrect decisions. You want this to be low as possible. And we are comparing versus an oracle, the purple line in the bottom. Oracle is the one that has access to all of the data. And even oracle is not perfect because the true model may not be a generalized linear model. So even an oracle that has access to all the data and responses for a new patient will make about 33% mistakes. Physicians' standard guideline, which says put every patient on the medium dose and then based on INR ratio adjust, is going to have about 45% mistakes. And the top curve is the UCB algorithm, OFUL. It's one of the best UCB algorithms for linear bandits and applicable here. Is actually very conservative because they're designed for worst case patients, not when patients like here can actually be independent, conditional on the covariates. And what we do see here is greedy is actually great. It's the green curve, but it does switch. Greedy first switches, the orange dashed curve is the greedy first. Switches because when we looked at the data, actually greedy will, if there were like much more patients, say 10,000 patients, eventually greedy first would have beat greedy. But this is just a demonstration that sticking to greedy decision making, you can outperform Thompson sampling as well as UCB and physicians.